Well, welcome to the last lecture of Essential Perturbation Theory and Asymptotic Analysis. This is the second and last slide deck for Chapter 6, where we're talking about WKB methods. Today we're going to talk about two subjects, and I don't expect to take the full amount of time that we usually take. Well, the first topic we'll talk about is the quantum harmonic oscillator, and I'm not going to go into a lot of the quantum mechanics behind this. There are a lot of good books out there. I've been lately reading this very nice book by David Griffiths, which is the standard undergraduate text and introduction to quantum mechanics. So a lot of the information can be found there. Are there any questions before we get started in this topic? All right, if not, we'll get started. Quantum mechanics and the simple quantum harmonic oscillator. And by the way, I forgot to mention, so the second topic that we'll be discussing is the two turning point problem. And the reason why I wanted to go through the quantum harmonic oscillator is because that's a really good motivation for what we're doing with the two turning point problem. So we're going to start with the time-dependent Schrodinger equation. This is a partial differential equation. I times Planck's constant times the partial derivative of this thing called the wave function with respect to time is equal to the Hamiltonian of the wave function, which comes in two pieces. So the first one is essentially the momentum operator. It's h bar squared, Planck's constant, divided by 2m, which is to say, well, m is the mass of the particle. In quantum mechanics, we represent a particle through a wave function. The particle no longer has or is thought of as a point mass, but as a wave function. The mass of the particle is still the same, 2m. It's just not localized to any specific point in time or space per se. This momentum operator involves the second partial derivative of the wave function with respect to x. And then we add to that the V, which is the potential energy of the particle. In this case, we're only assuming that V is a function of x, the spatial position, times psi. So the wave function, the way we want to think about the wave function is something which varies in time and space. It can be signed. We're going to do something with this wave function to try to understand how the particle is moving through time and space. According to I think it's the Born rule, we interpret the wave function in the following way. If we want to understand where the particle is in any point in time and space, let's say if we want to understand where the particle is with respect to these points A and B, then if we integrate the wave function from A to B, not the wave function itself, but the square of the wave function, or better yet, the modulus squared of the wave function between these 2 points A and B, then this should be the probability that the point is going to be found in that interval from A to B. The probability of finding this point in this interval A to B at the function or at this position in time. So this probability is evolving in time. But if we integrate over all of space, this wave function squared, okay, according to the Born interpretation of quantum mechanics, the probability that we find the particle somewhere should add up to exactly 1. So this is sometimes called the normalization condition. So we expect the wave function to satisfy the integral from minus infinity to infinity modulus squared wave function should be always equal to 1. Now, this is the time-dependent Schrodinger equation. The way we're going to solve this in this very simple situation where we're only assuming that space is one-dimensional, the way we're going to solve this is by using the technique of separation of variables. So we're going to first start out by assuming that the wave function can be decomposed into a spatial wave function times a function which only depends on t, the time dependence, and the spatial dependence of the wave function are separable. If this is true, then plugging this assumption into the time-dependent Schrodinger equation, we can produce this equation. Basically, what we're doing here is moving everything that has to do with time dependence onto the left-hand side, and everything which depends only on space to the right-hand side. Now, this is where it becomes very important that we assume that the potential V only depends upon X. If this is the case, then we can separate these two equations because this only depends on time, this only depends on space. So the only way for these things to actually be equal to each other is if they equal a separation constant, which is independent of both time and space. The separation constant is labeled E for an important reason. That's because later on we're going to show, or later on you would show if you deep dive into quantum mechanics, that this energy or this E separation constant is related to the total energy of the system. And so we are going to use this E as the separation constant. We'll later also show that E is quantized in certain particular cases, and E is going to be positive. But for now, we'll assume those two things, or at least assume this particular property that the energy is positive and independent of time and space, so that this equation here can be integrated exactly. And therefore, we could come up with the solution for a function t. T is capital T is a function only of time. It's just going to be exponential in time according to this relation. By the way, this I here really is the complex unit, so the square root of -1. Now, this equation, the spatial equation, isn't as easy to solve as the temporal one, but it transforms into something which looks like this. And this is sometimes called the time-independent Schrodinger equation. So the idea is that you're to find both E and psi, so this equation is satisfied. As long as we can find such an E, then we know that the temporal equation can always be satisfied. The temporal equation does not determine the energy levels. Only the spatial equation, the spatial or the time-independent Schrodinger equation, is going to determine the energy level E, or what those values should be. The psi is also going to be determined through the equation. So this, you can see, is more or less a classical eigenvalue, eigenvector problem. So we've got to determine psi and E so that this equation is satisfied. Now we're going to assume that the potential is that of a simple harmonic oscillator. So if this was a classical problem and we use the simple harmonic oscillator, we'd be solving an equation which looks something like this. I hope I get the sign right on this, but I think it is going to be m times x equals minus v prime of x. So in this case, minus v prime of x is just going to be, let's see. I'm wondering if I really should have this m here. I think I have to divide by m to get the units to be correct. But in any case, it should work out to be something like I'm going to just disregard that. we should get an equation which looks something like this, which has the solutions of sines and cosines. Okay. So this would be the case where we have a mass connected to a spring, and we give this mass a little bit of a displacement, and then it just oscillates back and forth forever. So that would be the case of having a classical harmonic oscillator. In the case of the quantum, we still have the same potential, but we plug it into the time independent or the time dependent Schrodinger equation in order to solve the wave function as a function of time and space. And this will determine the position of the particle, but not exactly. So we then need to solve this equation if we assume that we have the potential for the harmonic oscillator. We have to determine both E, the separation constant, or in other words, the energy, and the wave function, the spatial only wave function, lowercase psi. So this again is an eigenvalue problem that we have to solve. What are the boundary conditions that we use to solve this this eigenvalue equation? And how do we determine that we have a unique solution in these cases? Well, first of all, to answer the boundary condition question, we're going to we desire that the wave function satisfies this boundary condition. Or this isn't really a boundary condition because there actually is no boundary. But we're going to require that the wave function is zero as x approaches plus or minus infinity. So this gives us kind of boundary conditions, but this isn't going to fix the value of the eigenfunction or the psi function uniquely. The way we do that is because this is physics and we have to have an exact answer for the wave function, we use the normalization condition. So the normalization condition says that the time-dependent wave function has to be normalized according to our Born rule. But we know what this wave function is. It's just the product of an exponentially, well, let's see, how do I say this? A time-dependent function which depends exponentially on time times some unknown as yet spatial wave function. And of course, we're dealing with the modulus squared. So the way we deal with this is we multiply the function times its complex conjugate. When we do that, when we conjugate the time-dependent part, we change the exponent from minus I to plus I. But then when we do that, we see that this term cancels this term. And in the middle, we only have the modulus squared of the wave function. So this says to get your physical answer out in the end, the lowercase phi or psi, the time independent wave function, must also be normalized. So this will uniquely determine our wave function for us. But we know in general, if we're dealing with eigenvalue problems, the eigenvalues are uniquely determined, but the eigenfunctions are not necessarily uniquely determined. The normalization condition fixes that. The solution to this eigenvalue problem is well known. I'd like to use the word classical, but I don't want to confuse the topics. So it's known classically what the solutions are, but it's not the solution to the classical mechanics problem. It's a classical solution to the quantum mechanics problem. And of course, this solution involves these objects called the Hermite polynomials. If you've seen this before from quantum mechanics, or maybe if you've studied orthogonal polynomials before, you've seen this. It turns out that the eigenvalues are quantized, and this is not maybe surprising to us that the eigenvalues would be quantized. If you studied the quantum mechanical condition of a particle in a box, you know that the energy levels there are quantized. For this harmonic oscillator, you have quantization of the energy levels. And the whole reason why the quantization comes out is because precisely these eigenvalues come in these discrete quantities. In any case, you find that the energy levels, the eigenvalues, are En, which is equal to n plus a half times the Planck constant times omega, which is the frequency. Well, it's not really the frequency, but it's related to the frequency of the oscillation of the harmonic oscillator, where n is equal to 0, 1, 2, so it's all the non-negative integers. So we see that the lowest energy level that you can achieve in the quantum mechanical harmonic oscillator system, the so-called 0-point energy, is non-zero. So that says that this quantum mechanical system has some sort of intrinsic energy in it. So if I plug in n equals 0, you see that you get 1/2 h bar omega. The corresponding eigenvalues or eigenfunctions, sorry, are given by this long formula, where these h functions are the so-called Hermite polynomials. Notice that to this, or multiplied to these Hermite polynomials, we also have some normalization constants, and I'll show you where these come from momentarily, and a Gaussian. So polynomials, by their nature, are sort of wiggly oscillatory things. So you can imagine what the picture looks like. I have a polynomial part, which is oscillating, and I'm going to multiply that times a Gaussian. And we know what Gaussians look like. They're peaked, and then, of course, they trail away to 0. And the product of these two things is something which looks like this. Okay, so the wave functions, so this might be for the case, I don't know, n equals 3, maybe 4. The wave functions for the simple harmonic oscillator look like this. So they have some sort of Gaussian peak part, oscillatory part multiplied together, and then they trail off to 0. So that's entirely encapsulated in this description of the function. Now, I'm going to show you in a moment what these Hermite polynomials look like. But the normalization condition for the Hermite polynomials, that thing which determines what these constants out in front should be, is the following. So if I multiply the nth Hermite polynomial times the mth Hermite polynomial and integrate those two against this Gaussian, then I get some constant which depends in a complicated way on n at times the Kronecker delta. So they're orthogonal with respect to this weight function. The weight function for the Hermite polynomials is a Gaussian. And the normalization coefficients are given by this formula. So the first thing you might want to check is there's not much checking to do here. You could check that if I put these two objects back into this equation, then I satisfy this equation pointwise. You can do that and you'll find it. But the one thing I do want to check is that we actually have the correct normalization for this wave function. All right, so we'll do that in a second. The Hermite polynomials are a pretty standard system of orthogonal polynomials. If you've studied quantum mechanics, you've seen these before. The main way or the main application of Hermite polynomials is via the theory of quantum mechanics, in particular the study of the quantum harmonic oscillator. As I said, they form a system of orthonormal polynomials, or at least orthogonal polynomials, with respect to the Gaussian as the weight function. The interval over which these polynomials are defined, quote unquote, is the infinite interval minus infinity to plus infinity. So this is not, so The theory here is still guided by the Sturm-Liouville theory that we discussed a couple of lectures ago. The big difference is it's not a regular Sturm-Liouville problem. And there are a couple of reasons why this is the case. The biggest and most evident reason why it's the case is because the interval over which the problem is defined is infinite rather than finite. And you'll recall that when we discussed or looked at the Sturm-Liouville problem, that it was only for, in the regular case, it was only for a finite interval. So these are the first 10 Hermite polynomials, and if you want to plug these into Mathematica to check, you can verify pretty easily that they satisfy this orthonormality condition. We won't check that, but I did want to check that the normalization condition is indeed true. That is, if I give you, or if I claim that this is my eigenfunctions, then they have to satisfy a couple of things, right? They satisfy the boundary conditions, so-called, because, well, we don't really have a boundary, but it's how the values are tending towards the infinite boundaries, and also satisfies the normalization condition, which fixes the the shape of the function. So I did want to check that. So if I plug in the stated values for the eigenfunctions, then I get some sort of integral condition like this. And then if I plug in my normalization from here, from 4, then I immediately see that I get the nice cancellation that I want, and I get a 1 as desired. Now, more generally, it's not hard to show this is the condition when I'm integrating psi n against itself. But if I integrate psi n against any psi m, I won't get 1 in general. I'll get 0, and only get 1 whenever m and n are equal to each other. Now, how do we use this to solve the time-dependent problem, and why is it so important? Well, the reason why this is so important is the principle of superposition. Mathematically, we're just using the idea of the Fourier expansions, but in physics, it's called the principle of superposition, which says that, well, the solution that we proposed, the solution ansatz that we proposed, wasn't necessarily very general. We assumed at the very beginning that capital psi was equal to some spatial wave function times some temporal function. But in general, we can't expect solutions to be that simple in nature. However, in at least in one dimension, and it turns out to be true in higher dimensions as well, we can show that a general function is essentially a linear combination of functions of that type. The temporal function times the spatial wave function times a constant, where we sum from k equals 0 up to infinity. Now, the only question then is, how do you determine what these coefficients are in this expansion via the principle of superposition? And mathematicians call these guys Fourier coefficients, or generalized Fourier coefficients, and we know how to determine them. Physicists might use a separate or different little trick to get this this expansion, but the basic idea is this. All you do is you set t equal to 0. If you set t equals to 0, this term just becomes a 1. And so usually the thing at t equals 0 are what is called the initial conditions. So this is going to be the initial shape of the wave function, at t equals 0. So some people say, quantum mechanics says that the world is not deterministic. In fact, that's not true at all. Quantum mechanics is quite deterministic because the Schrodinger equation is deterministic. Now, it's how you interpret the wave function afterwards, which really throws into question whether or not things are really deterministic or not. The Schrodinger equation is a deterministic equation. If I give you precise initial conditions, then and I give you all the information that you need in the universe, the correct potentials and the interactions and everything, and I solve the Schrodinger equation, then it tells me what the wave function is like at some later point in time. And that's a completely deterministic problem. Of course, then there's this interpretation of quantum mechanics, which says what the Born interpretation in particular, which says what, well, if you want to locate a particle, all that we can know is the wave function, and therefore all that we can know is really the probability of finding a particle at a certain point. And that is true. However, don't mistake that with the point that the Schrodinger equation itself is completely deterministic. If I give you initial conditions, then I can tell you what the wave function is like for all eternity. Now, how do I determine the CK? We said that if t is equal to 0, that term just becomes a 1, so this is evidently collapses to that. Well, we use the orthonormality condition. So the trick, if you want to call it that, it's not very mathematically rigorous, but the trick is multiply both sides uh, by psi. What do I want to multiply it by? Psi L bar and integrate from minus infinity to infinity. And then use the orthonormality condition of the wave functions, and that's going to pop out the CL. Okay. And so the CL is just determined by integrating minus infinity to infinity of f of x against any of the wave functions psi L. So these are there's no mystery here. These are really just the Fourier coefficients or the generalized Fourier coefficients where we've used an orthonormality condition. Now, the problem that we just posed, the time-independent problem that we just posed, can be non-dimensionalized and put in a form which looks more or less like the problems that we've been studying. In particular, we can non-dimensionalize the problem to get rid of all the extraneous constants, and effectively we can produce an equation which looks like this. So second time derivative of y, so y is the new dependent variable that replaces the spatial wave function, which is equal to psi squared minus k. K is now playing the role of the energy. This is playing the role of the potential times y. And so what we want to do with the WKB method is generalize the solution for problems which look like this. So in the generalized methodology, we might not know that this is precisely quadratic. It might be something a bit more general, which we're going to take up in a moment. So for the quantum harmonic oscillator, we can solve this problem exactly. We know what the eigenfunctions are. We know that the energy levels are quantized, and we know how to compute them. But if this is replaced by something general, which has more or less the same structure, but in a general sense, then we don't have exact solutions anymore. And the best thing that we can do is use the WKB method or methods like that to approximate the solutions to that. So that's what we want to do in the next section when we talk about two turning points. So let's see if we can generalize that last problem a bit. So here we're going to consider the following Schrodinger, quote unquote, type equation. It's a Schrodinger equation, kind of a time-independent Schrodinger type equation. We're going to include the possibility that we have an epsilon term up front, where epsilon is a small parameter. Y satisfies usual boundary conditions that as x goes to minus infinity, y is approaching 0, and as x approaches plus infinity, y is approaching 0. In this case, we're going to be interested in getting an approximation to this problem on the domain minus infinity to infinity. But now we're going to assume that Q can change signs 2 times on the domain. Previously, in the one turning point case, we examined a methodology for solving or approximating the case where Q has a single turning point, So it crossed 0 exactly one time, namely at the point x equals 0. Q is positive in this region and negative in this region. In this case, in the present case, we're going to be interested in approximating the solution whenever Q looks like this. It has two places where it's crossing the x-axis, exactly two places. Specifically, we're going to take Q to be of this form. Now, in the quantum harmonic oscillator, with modulo some constants, in the quantum harmonic oscillator case, it's just going to be x squared minus e. So we're going to generalize that a bit. So, well, it'd be nice to know in what way we want to generalize it. Well, first of all, x squared is a function which looks like this. It's parabolic. It has a global minimum at x equals 0. As x goes to plus infinity, the potential goes to plus infinity. As x goes to minus infinity, the potential again goes to plus infinity. And if E is any energy level, right, which is positive, then the function V minus E has exactly two zeros, namely a 0 here and a 0 there. So we're going to generalize the case where V is quadratic only. So let's consider this. Suppose that V is simply a positive function or non-negative function that has a global minimum at a point C. I should say probably a unique global minimum. And if I plug in C, I get 0. So its minimum is at the point x equals C, and in fact, the value of V at C is equal to 0. This one isn't necessary to do, but it's kind of useful. We're going to assume that VR is monotonically increasing as R increases. So as you go away from, well, I should say what R is first. R is the distance between X and C, or in other words, in this very simple case, the absolute value of X minus C. So I could think about it like this. If this is my generic potential here, so that's going to be C. So R increases this way and R increases this way. Okay, as I go away from C, then the distance from C gets increases no matter which direction I go away from C. So V should be monotonically increasing this way and also this way. And it monotonically increases in the following way. It's going to go off to infinity. It can't monotonically increase to an asymptote, okay, here or here. It's got to really increase up to positive infinity going in either direction. So a very simple example of this might be a function which looks like this: absolute value of x minus c raised to some positive power p. That would certainly satisfy the conditions that we have here. Any potential V that satisfies this is what we're going to call single well potential energy. And you can have double well potential energies and triple well potential energies, but this one's the most important one for our purposes. The single well potential energy. And essentially it looks like this. It's a generalized parabola. So it follows that if we have a generalized parabola for our potential, then there's going to be exactly 2 points for every given positive energy where the Q function, which is V minus E, is exactly equal to 0. Okay, so a question in the chat is, do we mean that the distribution of the position of the particle is deterministic, or is it just the position as a random variable? So, uh, what I'm saying about the question of determinism is that the Schrodinger equation is 100% deterministic. If you tell me what the wave function is exactly at an initial time, and you tell me exactly what the potential is, or how to find the potentials, then I can tell you what the wave function is at any later point in time. However, according to the Born rule, the wave function really only dictates the probability of finding a point at a certain location in time. So if I solve and find the wave function at some time t equals 10 minutes, then that only tells me a probability density. And that only the probability density only dictates the probability of finding that particle at that fixed time t equals 10 seconds. And it's a spatial probability. Essentially, if I look in this, for that fixed time, if I look between a equals 2 and a equals 7, and I integrate that density function, then that should really be the probability of finding the particle there. So what does that mean in terms of probability? It means that if I have a system which is identically prepared, a system which has the same wave function describing the same set of particles, and I repeat that experiment identically prepared 100 times, then I should see that probability playing out exactly. Or in other words, it really should be the probability of finding the particle at that position at that particular time. So I hope that answers the question. I'm not an expert in quantum mechanics in any way, but I just did want to make clear that the Schrodinger equation and the wave function itself are deterministic objects. There's no randomness associated with those. The only randomness that's associated with the Schrodinger equation is then when you go to look for a particle, the interpretation of the wave function or the square of the wave function as a probability density, that's where the randomness comes in. Okay, so now when we go to solve this problem now, we're going to identify 3 regions. So now let's go back to our Q problem. So now our Q function looks like this. Previously, our Q function had only looked like this. Okay, it had a place where it was negative and a place where it was positive, and it was negative over here completely and positive over here. Now you can see we have a different set of conditions. Now we're going to have 3 regions essentially for this problem. So we have the region alpha to beta, where Q is going to be negative. Then we have the region where X is bigger than beta. And in that region, Q is positive. And then another region where Q is positive if X is less than alpha. So that's precisely quantified in these 3 conditions. Q is positive over here, minus infinity to alpha. It's negative between alpha and beta. And again, it's positive on this interval, beta to infinity. Now, when we looked at the single turning point problem, we built up connection formula representing this case. We can also build up connection formula representing that case. Okay, so we kind of just have to do a little bit of a flip to get that right, the right directionality of it. Then the only question is, well, now we have 2 descriptions of what's going on in this alpha to beta region, okay? And they're going to be oscillatory type solutions. Now all we have to do is kind of join them up. And if we do that, then that should give us a uniform WKB approximation. Now, it turns out what happens when you try to join them up in this regime right here, then this is what gives us or gives rise to the quantization in the WKB approximation method. So maybe a picture would help us to understand what's going on here. So let's look at that. All right, so there's our Q function. And we know what the solution is going to look like more or less in this region, okay, or around this point. So it looks like an oscillatory solution with a decay. And then a decaying solution. On the other hand, we have a sort of similar thing with respect to this turning point. We have an oscillatory solution, so, and a decaying part of the solution. So the decaying part looks like this, and then, okay, that doesn't look too bad. Now, I'm going to have some adjustment parameters available to me, and the adjustment parameters are basically going to be there so that I can link up these two forms of the solution here. And that is going to give rise to quantization in this case. So let's see how this works. So we have two connection formula. So one is out here near beta and one is near alpha. And we have essentially three regions associated to each. There's some sort of inner expansion region where the Airy functions were important. So that I'm going to call the region omega I for interface beta. So that's where the Airy function is valid. Then we have a decaying region. That's going to be this part of the solution. And that's going to hold, with some overlap, basically in this part of the domain. And then there's going to be some part of the region which is spatially oscillatory. And that's going to be basically this region here. Now, I should point out that really I'm building this part of the solution near beta under the assumptions that basically near beta, Q looks like a single turning point problem, right? It goes through zero. It has some slope here. So the slope of that function I'm going to say, or I'm going to call A beta, A subscript beta, and locally around beta, in fact, as x goes to beta, this has the asymptotic relation or expansion A beta x minus beta plus big O of x minus beta squared. And just because we can choose the sign of this. This should be a positive sign. Now remember, there was one constant that was available otherwise. That was the A constant. We're going to call that alpha beta for the one associated to this side. Everything else is more or less exactly the same as it was for the one turning point problem. So this just comes from our connection formula for the one turning point. The representation of the solution near x equals alpha is a bit harder because it kind of is like coming up with the approximation by standing on your head. So we have, or at least looking in a mirror. That might be a better way of putting it. Because the function q is kind of reversed from what it was previously. And more than that, so this q function is not centered at x equals 0. We've got to shift it around so that it's centered now at x equals alpha. So that's kind of complicated. It took me a while looking at these, staring at these formulas to get it right. But basically, the idea is this. I'm going to assume that q has the representation near alpha as minus a alpha, where a alpha is, again, a positive number. So q is minus a alpha, x minus alpha. That means it has a 0 at x equals alpha. And its slope is basically negative. And the slope is going to be minus a alpha, where, again, a alpha is positive. And the only deviation from that is some sort of higher order, second order deviation, okay, which we're going to cram into this big O of x minus alpha term, x minus alpha squared. All right, now this one has a solution part where it's going to be exponentially decaying, right? Then you have the area connection, and then you have an oscillatory portion. But it's reverse to what was the shape of the solution around x equals beta. Remember, the decaying portion was, it decayed that way, and then it oscillated in this way. So you have to do a little bit of flipping and manipulating. And at the end of the day, so we want our exponentially decreasing part out here, and it should be exponentially decreasing as x goes to minus infinity. So it should decrease that way, in that direction. Okay, so it's set up to do exactly that. And then you have your area connection function. And then finally, you have your sinusoidal function. Okay, so this guy should oscillate that way. So it should oscillate this way, and it should also decay as x goes or gets larger in that direction. And all of this, I claim, is contrived to do exactly that. All right, now, well, we have two solutions in the A to beta range, or sorry, alpha to beta range. And they're both oscillatory. So one was coming from this side. So it's decaying, and then it's oscillating, and it's decreasing oscillations. And same over here, but maybe I'll give that a slightly different color. So now, so we've got one representation and another representation. So deep in the center, those two representations have to be the same because it's the approximation should be the same. So the easiest way to do this is just to join these two solutions over the entire interval. And so this is the representation of the solution near beta, and this is the solution near alpha from this side. So I just want to make them exactly equal on the interval alpha to beta. So this is what we call the quantization condition, because we shouldn't imagine that this could hold in general, because there's nothing to say that they should. And you'll see that certain conditions have to hold in order for those to be equal to each other. But notice what we've got to play around with. The integration limits here are different than they are here. The functions are the same everywhere. It's still the same Q function. And then these two coefficients, A beta, A alpha, are different in general. So we have to try to set up the problem so that everything is equal. So to do this, it is useful for us to define a few things. So notice that this guy in here, okay, this looks like an integral. So I'm going to define, well, it is an integral, it's almost the integral from alpha to beta. So I'm going to define the full integral from alpha to beta. Okay, to be equal to this thing called k alpha beta. So I think, yeah. So this is actually pi over 2. It's a little bit different than what we have appearing here, which is a pi over 4. We'll see where this comes into play in a moment. Okay, so I'm going to define this k alpha beta. I think that this is correct, but we're going to have to double check and make sure. And of course, these things here, I alpha, I beta, are just the integrals that appear, the sign plus the integral. So that's just these things here. Okay. So what do we need to make these two things equal? Well, we need these coefficients to equal. The 2's definitely equal, no problem. But, and the denominators are equal, right? Because those are the same things. What we really need to make equal to make all these things work is a beta times this integral should be equal to a alpha times this integral. Okay, so the quantization condition 11 is exactly equivalent to saying that a beta I beta of x should be equal to a alpha I alpha of x for each x in the interval alpha to beta. Okay, so that's what we need to make happen, and this is going to be a useful quantity for making that happen. So I think what we start with is I beta. Yeah, that's what we start with. So let's start with I beta. I beta is the sine of 1 over epsilon integral from x to beta of the square root of minus qt plus pi by 4. So I'm going to manipulate this in a little way. Let's show, actually it's kind of clear that this integral can be split into two integrations. The integral from alpha to beta minus the integral from alpha to x. Right? So if I subtract off that part, this integral part from here, that's clearly equal to the integral from x to beta. Okay, so this is more or less a trivial splitting. The nice thing about this now, though, is that this is independent of x, and I can control that a little bit more easily. The next thing I'm going to do is multiply by a minus sign out front and use the fact that the sine function is an odd function. If I multiply by a minus sign out front, I can make the whole thing equal by putting a minus sign inside the argument. Or in other words, minus the sine of x, minus the sine of minus x is equal to the sine of x. Use the fact that sine is an odd function. Okay, so if I do that, then I flip the sign on these two integrals. Flip the sign there, and flip the sign on this. Next thing I'm going to do is I'm going to pull this term away. I need this term here to be a term beside this. If I'm going to make this equal to I alpha, I need this to be a plus pi over 4, not a minus pi over 4. So I'm just going to add what I need. I need it to be plus pi over 4. And if I add a pi over 4, I have to subtract pi over 4, so the whole thing becomes minus pi over 2 over here. Now, the reason why I'm trying to make this look like the integral from alpha to x is because that's what appears in the I alpha integral, okay, or the I alpha term. So that's an integral alpha to x. So that's why I'm trying to make it look like that. And notice that it has a plus pi over 4, so I've added that. Okay, so now we're just going to use the sine angle addition formula, right? Sine of theta plus phi is equal to the sine of theta cosine of phi, et cetera, et cetera. So the sine angle addition formula says that this sine of these two angles, I'm going to split it like this. this guy here is my angle K alpha beta, or minus K alpha beta. So I get minus the sine of the first angle times the cosine of the second, or you could think about it as cosine of minus the second, but use the fact that the cosine is even, plus the cosine of this whole bit, or no, cosine of this bit times the sine of that bit. And of course, you have to double check that my signage is correct, but I believe it is. So in any case, I've just shown that I beta is equal to I alpha of x times cosine k alpha beta, from this term, plus cosine something which looks reasonable times sine of k alpha beta, where again, k alpha beta is all this. So this is minus k alpha beta here. Now, I really want my quantization condition to hold, right? So what I really want is for this guy to become a 1, plus or minus 1, I guess, and this guy to become 0. That's the only way that this can hold in general. So really I need sine of k alpha beta to be 0. That's essentially a quantization type of rule, as we'll see in a moment, because the sine is equal to 0 at certain increments of this angle k alpha beta. In particular, k alpha beta should be equal to pi times k, where pi is of course the usual constant pi and k is some integer. Now we can look at k alpha beta and let's think about what values of k these could be. Now, actually, we can show that pretty easily. K alpha beta is actually positive. K alpha beta is positive. That means all of this is positive. That's because this is a positive quantity. We're integrating over a positive interval. This is a positive quantity, so this has to be positive. So now we know that k can be, it can't be equal to 0. The best it can be, or the lowest it can be, is equal to 1, 2, etc. So we've not only quantized it, but we found out what what the smallest energy level could be. Let's go a little bit further. If we plug in what Q is defined as V minus E. So minus Q is going to be E minus V. So we have 1 over alpha integrating from alpha to beta of the square root of EK minus V. That should be quantized according to our rule. Basically, I've taken this, moved it to the other side, and simplified a little bit. So we get K minus a half pi for K equals 1 to up to infinity. And I've written here that I've added the extra index K because now we know that the only way that, this is a function. There's no quantization allowed on that. There's no free parameters. The only thing that could be quantized in this case are the energy levels themselves. So that's why I've added this subscript K. This last equation here is what I call, at least, the first quantization rule, because that tells us what the allowable energies are. This is the only way that we can get a connection formula. This is the only way we can make this thing something like this. This whole thing has to go away, and the only way it can go away is if this is 0. So that's our first quantization rule. The second quantization rule, well, if that extra term is gone, this extra term is gone, and what we really want is A beta times I beta is equal to A alpha I alpha. So let's see if we get this right. So, oh yeah, one more thing. So before I get onto that, if this term here is really 0, we're choosing angles to make it so. That choice is going to make this plus or minus 1. In particular, it's going to be cosine k pi for k equals to 1, 2, etc. And so this just becomes minus 1 to the k power, this whole term here. So therefore, our quantization condition can be expressed as A beta times -1 to the K has to be equal to A alpha. That's because we have I beta and I alpha on the other side, but they, well, I guess we only have I alpha. So I alpha, and I canceled those out. So this is what is called the second quantization rule. It tells us what our coefficients can be out front. So we have the energy levels are quantized, but then to make the connections precise, we have to choose A beta times -1 to the K power equal to A alpha. And that really connects those two formula up. So remember what's happening here is here's x equals alpha, x equals beta, and now we've got them perfectly synced up so that they really do connect perfectly in the center there. That's actually a very nice picture. I'm proud of myself for that one. So the way that this works is we need two quantization rules to do this. The one dictates the quantization of the energy, and the second one shows you how to choose these coefficients. Now, I have to point out, when is this valid? So the problem that we're solving, these problems don't always have an epsilon in front of them. In fact, if you go back and look at the non-dimensionalized version of this problem, what we were looking at was a problem which looked like this. I forget, this is plus or minus, I can't remember. There was no epsilon squared here, it was gone. So what does that mean? That means that, well, if there was an epsilon here, and that epsilon was small, our WKB approximations would be valid. However, when we were discussing the Sturm-Liouville problems, we argued that our approximations are also valid if the eigenvalues are large. Okay, so there's two scenarios in which, and they turn out in quantum mechanics to be highly related to each other. There are two scenarios where we could have these WKB approximations be valid. The first one is that epsilon is small, and the second one is that the energy levels are high. And actually, you could have both of these things being true simultaneously. We only need one of them. For our applications, we're going to mainly consider the case where the energy levels are high and the epsilon is normalized to just be equal to 1. So this isn't the greatest example in the world. I think I could come up with some more interesting ones, but this one just basically shows that our WKV method is on the right track and is valid in a certain sense or for a certain problem. So we look at the problem at the beginning of this section, which was this one here. We're going to set epsilon equal to 1, and we're going to pick the v inside this q function. Remember, q is defined as v minus epsilon, or v minus energy, E. Let's just pick this v to be the quadratic function, or in other words, the harmonic oscillator potential. We already know what the solutions are in this case. So again, setting epsilon equal to 1, taking v to be the harmonic oscillator potential. We already know what the solutions are in this case because this is the classical quantum, or the quantum harmonic oscillator. I shouldn't say classical. The quantum harmonic oscillator. And And so we know what the eigenvalues are. We know that the eigenfunctions are given through these Hermite polynomial functions, etc. But let's analyze this without knowing that or pretending we don't know that and use the WKB method. Well, in this case, if v is chosen as x squared, then we can right away say what alpha and beta are. Alpha is equal to minus the square root of energy, and beta is equal to the plus square root of the energy. Right? So, and I've thrown in here that we know already that the energy levels are quantized. Q is equal to x squared minus E, and alpha and beta are determined precisely by setting this equal to 0. So beta is equal to the square root of E, and alpha is equal to minus the square root of E. So that's the setup. The quantization condition, the first quantization rule, says that 1 over epsilon, epsilon is equal to 1, integrating from alpha to beta, square root ek minus v should be equal to a certain formula. Well, to see that it's equal to that certain formula, let's compute this. We can, in this case, compute this exactly because this is quadratic. Let's do a simple change of variables. Actually, we'll do the change of variables. Right. We'll do that. Do the change of variables second. We can immediately in here remove this from the inside the square root. We can remove a constant factor of square root of E. We're integrating, of course, from minus square root of E to square root of E because that's what alpha and beta are. If we pull this all the way out front, then what we're left with in the integrand is this, 1 minus, or square root of 1 minus x over square root E, quantity squared. Remember, E is a positive number. Well, you can show that this is just related to the area under a semicircle, where it's a semicircle having these extents, radius square root of E. And of course, the area of half that circle is just going to be square root of E times pi by 2. So the total integral works out to be ek times pi by 2, because you have a square root of E times the square root of E. That's where this comes from. Now, the quantization rule says that that this should be equal to, well, let's go back because I've forgotten. Here's the quantization rule. It says that that integral should be equal to k minus a half times pi. K minus a half times pi. But we know what this integral is because we can compute it exactly. And so now we can solve exactly for the energies, the energy levels. And they work out to be 2 times k minus a half quantity, where k is equal to 1, 2, etc. But if you go back to the work we did on the quantum harmonic oscillator, we can deduce exactly the same things. In fact, the exact eigenvalues work out to be these numbers here, 2 times k plus a half, where instead of starting at k equals 1, you start off at k equals 0. That's just a counting problem. It doesn't really matter that you're starting at 0. In this case, these two sets of numbers are exactly the same. So in this case, the WKB method gives you the exactly correct energy levels. Now, I didn't do it, and I wish I had a few more minutes or a few, maybe actually to be more realistic, a couple of hours to compare my WKB approximation. Remember, that's given now in a bunch of different pieces. I'd like to compare the WKB approximation with the eigenfunctions that we know are correct. So for this non-dimensionalized version of this problem, the eigenfunctions work out to be like this. Remember, the main thing here is that they are Hermite polynomials times these Gaussians and normalized appropriately so that the normalization condition holds. I didn't do that calculation to figure out how close these match, but I imagine even for small values of k, that match pretty well because the energy levels come out to be matching exactly. I didn't do that, but if any of you are enterprising enough and interested, I'd love to see that plot in Mathematica. But the takeaway here is that a WKB method at least yields the exact eigenvalues. So it's in the sense of approximating the eigenvalues, it gets it exactly correct. So it's not an approximation at all, but an exact representation. Well, that is it. That is essential perturbation theory and asymptotic analysis. I wish that we had time to do the method of multiple scales. That's essentially the content of what is going to be chapter 7. Um, we don't have time to do that justice, so I won't even get started on that. And I'll rest my weary eyes from typing, give myself a little bit of a break anyway. Um, so we won't cover that here, but if you come back for a later iteration of the course, maybe when you look it up on YouTube, it should be there. If you want to see what the method of multiple scales is, then the course that's ably given by Dr. Strogatz, that we've cited in various locations, explains it quite well, and many books do an exceptional job of that as well. So I'll stop there, and if you have any questions about anything or comments, stay on the line, stay on Zoom for a while. And if you got to go, no problem. Go ahead and send me an email. But otherwise, I hope that you have a good day, and I hope that you have a productive and fun summer, relaxing. And I'll see you guys soon.